Hey, what's up, everybody? This is Mr. Murray back on Mr. Murray's Mathland, doing another classic related rates question for calculus, and this is a shadow problem. So it's a fairly common one. The height of the person changes, the height of the lamppost changes, but uh, fairly common question here. So let's just get right into it. Most textbooks have a variation on this problem as homework, and sometimes kids find it a little confusing. So here we go. A 6 foot tall man's walking away from a 28-foot tall light pole at a speed of 5 feet per second. Find the rate of change of the length of his shadow. So let's get a little diagram going so we can visualize this. So don't critique these art skills here. But there's our lamppost, our light pole, whatever you want to call it. And then we have a 6 foot tall man walking away from it, which is important. Okay, and so here is the light, and the beam of light is casting his shadow. And so his shadow's right here on the ground, this part right here. Okay, so let's label a few things here and see what we got here. So this is 28, the lamppost. The man is 6 feet tall. He's moving in this direction. And as always with related rates questions, you want to assign some variables and identify what you have and what you're trying to find. So he's walking away at a speed of 5 feet per second. So anything that's a rate is a d something dt, right? A derivative value. What part of the diagram is that specifically referring to changing? He's moving in this direction. That's referring to this distance, the distance between the man and the light post. So let's call that, a variable. Let's call that x. That way we can say dx dt is 5. And it's positive 5 because he's walking away, so it's getting bigger. If you were walking toward the light, it would be shrinking, and so it would be negative 5. And then the other thing we want is the rate of change of the length of his shadow. So that should be a pretty obvious, we'll call that y. You could call it s for shadow, but my s's look like 5, so I don't want to do that. So we are looking for dy dt. Okay, so hopefully you see what's going on here. If not, it's you've got similar triangles happening here. You've got this small triangle with the man and his shadow, and it's inside this larger triangle with the lamppost all the way to the tip of his shadow. So with similar triangles, you want to set up a proportion ratio between those sides. So here we go. And if you know your geometry well, you have a lot of freedom with how you set up these proportions as long as you are consistent with the corresponding parts. So I'm going to go this way. In the small triangle, 6 is to y. 6 is to y as 28 is to this bottom side. So 6 is to y as 28 is to this bottom segment. And what is that bottom segment? That's the sum of x plus y. So and if you were wondering, you could set up proportions like 28 is to 6 as x plus y is to y, or something like that, as long as you're consistent again. So you've got this equation set up that uses x and y, and you have dx dt, you want dy dt. You could differentiate this right now, but you'll be using some quotient rule here on the right, or some chain rule or something. So why don't we clean this up and just do a little cross multiplying. So here we go. Distribute that. We'll get 6x plus 6y is equal to 28y. And while I'm at it, why don't I combine my like terms, subtract 6y from each side, and you'll have 6x equals 22y. And now I've got a lot nicer, a lot simpler equation to differentiate. So now I'll differentiate this, and remember, with related rates problems, you are usually doing it with respect to time. So anything that's not t, you need to use a d whatever, dt. So on the left side here, we're going to get 6 dx dt equals, on this side, 22 dy dt. All right, and now it's pretty much just plug in what you have and what you're solving for. So I know that dx dt is 5, so I'm just going to substitute 5 in for dx dt and solve for dy dt. So you'll have 30 and then divide by 22 to solve for that dy dt. Maybe reduce that, always good habits here, to 15 over 11. Okay, there's dy dt, and that is what you were looking for, the rate of change of a shadow. But with related rates, I always like to write a sentence. It's a word problem, so let's answer with words. And we were trying to describe the length, the rate of change of the length of his shadow. So the man's shadow, and I usually like to try to incorporate the word increasing or decreasing when what I found is a rate. So my rate is positive, meaning the shadow's getting longer. So the man's shadow is increasing. That's a positive rate of change. If it was a negative, I'd say decreasing. Is increasing at a rate of 15 elevenths. And what are the units in this? Feet per second. Okay, so there we go. Pretty short and sweet, pretty direct. Another twist on this is just, as kind of a footnote here, is that sometimes they'll ask not for the rate of change of the length of the shadow, but how fast is the tip of the shadow moving. And what's happening there, in case you encounter that, is that the man is walking, so the shadow is moving, but it's also getting longer on its own. So what you really are doing is the sum of his walking speed plus his shadow length speed. So if you were looking for how fast the tip was moving, you would take this 15 elevenths and then add in his walking speed, which is 5, and that gives you that cumulative total speed, or that tip is moving at. But they didn't ask for that here, but I thought I'd throw that in just for fun here, for those, to reward those people who are still listening to this. So all right, hang in there, kids, with the related rates, and keep working hard. Let me know if you got any questions.